Hello, this is Project 21071 on monoclonal antibody manufacturing. I am Tiffany Hamilton, and with me today I have Cody Liebeskind, Julia Moore, and Kayla Scarmella. Today we will begin with a poster preview and then discuss our goal and introduction of our project. Then we will give our process overview of our project, followed by overall economics and costing, and then any uncertainties, results, and recommendations. Here is our poster slides that we would have been using if we were in person for this presentation, but since we are online, we have presented it in one of our slides. If you would like to see some more information on this, please follow up with us following this presentation. The objective of this project was to create a simulation for the continuous production of monoclonal antibody treatments for metastatic breast cancer patients. Breast cancer patients are often not able to adequately produce antibodies to fight cancer. Lab-produced monoclonal antibodies, known as HER2 trastuzumab, can be used as a treatment. Current antibody manufacturing processes occur as a batch system, which results in product inconsistency and requires charging and discharging between reactor batches. Industrial antibody manufacturing processes require the attainment of monoclonal antibodies, which are produced through the insertion of an antigen into a mammalian cell. For this project, the monoclonal antibodies will be provided by a supplier. The cell-produced B lymphocytes, which produce immortal cells with the ability to produce antibodies, and then are humanized. Next, after ensuring a constant pH, temperature, and oxygen conditions for the culture, the mammalian cells are entered into a bioreactor, which is usually suspended in a liquid culture to produce the monoclonal antibodies. This project creates a continuous manufacturing simulation for monoclonal breast cancer antibodies, and thus a continuously stirred bioreactor will be used. The extracted antibodies are purified and concentrated to be used in medicinal products. The process includes obtaining a cell line to produce the antibodies, verify products, and prepare products for distribution. The target market for our product is patients that are diagnosed with metastatic breast cancer. In 2020, this was 275,000 Americans that were diagnosed with breast cancer, and 6% of those people were diagnosed with metastatic breast cancer. Next, Julia will give a process overview of our project.
Thank you, Tiffany. So here we have our process overview, which is our process flow diagram. As you can see, there's quite a bit going on here. So I'm just going to walk through a summary of some of the steps in our process. The process starts over here, where we have cooling water and steam coming from outside vendors, and we have our two initial storage vessels, which will hold all of the inputs for our bioreactor. Our inputs are loaded into our bioreactor, labeled R103, which is where our cells will be producing our antibodies. Our solution will then flow to our centrifuge, where the large cell pieces will be separated from the rest of our solution. Our feed will then pass through a series of chromatography, filtration, and other purification steps to remove impurities from our solution. The final stages of our purification process are ultrafiltration, diafiltration, down here with the blue arrow. At the end of this process, we should have antibodies and water left in our solution. We have a verification loop here labeled with liquid chromatography, where the concentration of our final product will be verified to make sure that we have all the impurities that we desire to remove out of our solution. The rest of our solution will then enter our spray dryer labeled D133, where a solution will be transformed from a liquid to a powder. That powder will be sent to packaging, where it will be placed into appropriately sized vials, and then it will be sent off to our final product storage before it is sent off for consumer use. Throughout the process, our waste is collected here in our autoclave labeled A137, which sterilizes our waste, and then our waste is sent to our final waste storage here. Throughout the process, we also have several pH, temperature, and flow rate monitors, which will be used to control the conditions of our process once this is built and running. Next, Cody will be discussing our process economics.
Thank you, Julia. So I'm going to be going over the overall economics and costing for this project. If we could focus our attention to the left side of the screen, we can see we have a table with the annual cost of the project in it. So right now I have all the major costs are displayed in this table, but I'm just going to hit the very most important values here. So the cost of manufacture for our process is going to be about $159 million per year. General expenses for the process, which are based on the sales of the process, are going to be about $1.06 billion per year. And the total cost of the process every year is going to be about $1.22 billion. Capital investment to get this project started is going to be handled in the upper right-hand corner of the screen. And here we can see all the different investment values. The most important of these is the one at the very bottom, total capital investment, which is $1.21 billion for this project. 3/4 of that cost actually comes from the cost of working capital, which is $944 million. If we can direct our attention now to the bottom right-hand side of the screen, we can see sales and profitability values for this project. So for this project, sales come out to be $1.96 billion, with a post-tax profit of $6.07 billion, an ROI of 5.0 or 500%, and a payback period of 0.009 years. All right, now I'm going to hand it off to Kayla to go over the conclusions or recommendations.
Thanks, Cody. So to wrap up, we're going to go through some of the uncertainties, results, and recommendations for our project. There were several assumptions made throughout the calculations and optimization process, but one that is more impactful to the economic results is the sale price of the antibodies. The actual sale price of our antibodies from business to business was unknown, but it was assumed to be about 50% of the final business to consumer price. As for results, our plant produced 1,680 kilograms of antibodies per year. The equipment required a maximum of about 580 million kilojoules per year to run, and our life cycle analysis revealed 449,000 metric tons of CO2 were emitted per year. For electricity usage, it was 3,660 metric tons of CO2 per year. Our plant made just over $9 billion in sales, which was about $6 billion after taxes, which was a return on investment of about 500%. Going forward, we recommend efforts to increase the product yield and cut costs. We suggest optimizing equipment further through a pilot program to reduce energy use, water consumption, and waste generation. We also recommend getting in contact with suppliers and buyers to fine-tune our economic estimates. This concludes our presentation. Thank you so much for taking the time to learn about our project.